This is, again, an archaeological session. We'll dig in the past. Anyway, so last time I described the general setup of momentum space analyticity in quantum field theory, and today I'll discuss precisely what Slava was talking about, namely the crossing property for the four-point function. So I'll start by an exercise in analytic completion. This is an example of a problem of an edge of the wedge problem. You have a function which is analytic in two tubes. These are the two tubes. This is in a two-dimensional space, a two-dimensional Minkowski space, and you have in the complex two-dimensional space, you have these two tubes. You have used the light-like coordinates, and first tube is defined by the imaginary V and imaginary U positive, past tube, imaginary V negative, imaginary U negative. And you have a region of coincidence of the boundary values from these two tubes, and I choose as the region of coincidence a double cone, just like this, which is also a topological product. So it is easy to solve this edge of the wedge problem like this. Instead of separating the real and imaginary parts, I look in the complex U plane, the complex V plane. The T plus is just the topological product of the two upper half planes. The T minus is the topological product of the two lower half planes, and the region of coincidence is the topological product of these two intervals. You change the variables in order to transform the upper half plane into a strip, and similarly for V, and after that you have the upper half, the future tube is transformed into a tube, which is this topological product here, imaginary V prime between 0 and pi, imaginary U prime between 0 and pi. The past tube is mapped here, and you apply the convex tube theorem to a case which is just a little bit limiting. I see that one doesn't. Can you see the convex closure of the two tubes here?
Yeah, we can kind of.
And okay, so you have the convex closure of these things, and this convex closure is the union of a family of topological products, a union of squares like this. And if you go back to the original variables, you see that you have the square which I drew is in this picture represented by the topological product of two disks, so it's a polydisk. This polydisk depends on the position of the square which I drew. The position of the square depends on an angle theta, which is between 0 and pi. And so the domain is the union of polydisks which depend on a parameter, theta, which varies between 0 and pi. In particular, the domain contains the polydisk where theta equals pi over 2. That would be the circle, the disk with diameter minus a. So you see that it is easy to solve this problem, and we'll need this exercise in the future. This example illustrates a phenomenon which happens sometimes, which is that you have a domain which is the union of two topological products, and very often you can represent the solution of this problem by an interpolating family of topological products. And another example is this one. In this case, I am sorry that one doesn't see the cars. In any case,
you can see it more or less. Don't worry. From your angle, it's not good, but from our angle, it's okay.
Okay. Well, here we have the union of two topological products. The first is a neighborhood of this real segment times the whole upper half plane here. And the second topological product is let's say, a half disk, and here the union of these real spaces. There is a little bit of analyticity above the real place. Again, you can solve this problem by using the tube theorem after making a change of variables. The original domain is represented by this flattened tube. You take its convex closure, which I did here, and again this convex closure is the union of some squares, which are topological products themselves. And if you go back to the original variables, you see that the square which I drew is the topological product of this lunule indexed by the angle theta over 2, and the outside of this also lunule, but the outside of it, and this is labeled by the angle theta, which is the double of this one. So, in fact, you see that if you go back to the original picture.
By the way, in the second equation on the right, the z should be a w in the right-hand side, just to, oh, I'm missing. No, where you were. W prime. You mean W prime as a function of W?
Yes, W prime, yeah, right. So, but you see that if you can interpret this in the following way: for every point of the original domain, there will be the outside of some circle which will depend on the position of this point. Okay, let's leave these exercises, but these exercises will be used if I succeed in getting to the end of my talk.
And so in these simple exercises, you are always able to reduce to the tube theorem.
Yes, but
Is this a general?
no. There are much more general cases. But if you know the tube theorem, you can solve a large number of exercises of this type. Okay. Now let's go to the four-point function. The four-point function is a function defined in the four-point momentum space. The four-point momentum space is defined inside the product of four Minkowski spaces by points such that the sum of the kg equals 0. That's the conservation of energy momentum. So this is the four-point momentum space. I'll limit myself to dimension 4, but it works exactly in the same way for any dimension above 2, not 2. 3 and above. 2 is a little more special because, for example, there is no scattering angle. But anyway, I'll limit myself to d equals 4. And so, as I discussed last time, you have in this space, you have some generalized retarded functions, which are these generalized retarded functions are labeled by things called cells, and each of them is the boundary value of a unique function which is analytic in a certain domain, and this particular retarded function is the boundary value from a particular tube. Okay, this is the Steiner planet. It's a picture of the various cells. You don't have to memorize it, just to show how these cells look like. Now, in this picture, you see that some cells are contiguous across some plane. One has to be careful that this does not mean that the corresponding tubes are adjacent across a plane, but they, for example, if you have this situation, two cells separated by a plane, it means that this cell is in the region where the K labeled by this subset Y is in the T plus, and the K on this side is in the T minus. So it's not just a one variable separation. It's not a. But in any case, this gives an intuition of what happens. So if you have two cells like this, which are adjacent along a face, then the two corresponding generalized retarded functions coincide in a certain real region. For example, in this case, Y is a subset of 1, 2, 3, 4. So if this subset is a two-element subset, the corresponding region of coincidence is given by this inequality. And if Y is a single, has only one element, then besides this condition, you must also avoid a discrete hyperboloid, which is a mass hyperboloid for the corresponding particle. So, and here, these things are called the thresholds. Now, here I drew the regions of coincidence. So this is the case for a subset which contains only one element. You see that it has, that the region of coincidence, P sub y has to be below this hyperboloid, but also it must avoid the one particle hyperboloid. If Y has two elements, you only have these hyperboloid. So to avoid these one particle hyperboloids which contribute poles to the momentum space functions, you replace the momentum space functions H by its product with these factors which remove the poles. And so it's with this function that we are going to deal. And in fact, it is this function which its boundary values which appear in the reduction formula.
So what are the stability conditions?
The stability, these are the stability conditions.
This big MJK.
MJK is the threshold here, you see. Here is MJK. M12, it's the parameter of this hyperboloid. So it characterized the region of coincidence.
Yeah,
It's a threshold in this channel. Below this threshold, you have a region of coincidence of the various retarded functions. Above, you don't.
Okay.
And in fact, the regions that you see here correspond to cuts, which in the framework of the linear program which we are dealing with are not crossable. These cuts are there. They are a limit for the domain of analyticity.
So you are saying your theorem is not going to assume that Mj and Mk are the lightest particles in their symmetry class.
Sorry?
So, for example, if Mj and Mk are the lightest particles in their symmetry class,
Yeah.
then big MJK is equal to the sum Mj plus Mk?
Or lower, because there might be other particles
Like bound states.
in the theory which give some extra trouble. Okay. So this is what yes. So if S and T are cells which are adjacent along this face, then the boundary values, the branches of the analytic function, which is the two branches which correspond to the two cells, HS and HT, they have a common analytic continuation in a certain little bridge above these regions of coincidence, and so this is why there is a single analytic function for the four-point function. Okay. Now, what we call the primitive domain of analyticity is the set of all the tubes that correspond to cells, plus these regions of coincidence which I just mentioned. And of course, everything is invariant under the real Lorentz group. So this primitive domain is invariant under the real Lorentz group. And because of the hypothesis which we make, namely that there is a minimum positive mass in the theory, there are no zero masses in the theory I consider. If there were zero masses, I could say nothing. So this is limited to non-zero masses, and under these conditions, this domain of analyticity, I mean, in fact, under these conditions, all the generalized retarded functions coincide in a common real region, and this real region contains the origin and is star-shaped with respect to the origin. So, as a consequence, the primitive domain is invariant. It contains zero, and it is star-shaped with respect to zero. And the consequence of this is that its envelope of holomorphy is also a star-shaped domain. In particular, it is schlicht. It doesn't have sheets. You can never... So, this is a very valuable property, because if you make some analytic continuation in some manner and you reach the same point by some other manner, you're assured to get the same result there. So that's a very important property. And another extremely important property is that in spite of the fact that I did not assume that my functions are Lorentz invariant, the domain, the envelope of holomorphy of delta is invariant under the complex Lorentz group. This is a consequence of a very important theorem by Glaser and Streeter. So this property is extremely, we could not proceed without this property. And I insist that I do not assume that the four-point function is itself invariant under the complex Lorentz group, because all this argument is valid also in the case of fields which are not strictly point-like, but which are localized in some finite regions. For example, if you have local observables, provided the fields are strictly localized in bounded regions, or if you have composite fields, which are simply convolution of several local fields, but which are needed to represent some particle, nevertheless, this business applies to this case. Okay.
Andrea, I don't understand, because I thought that the most interesting case when scattering amplitude is Lorentz invariant.
No, this is not the most important case. Well, can we...
We can discuss later.
discuss it later. It's a very simple thing. I mean, think of fields which are localized in bounded regions instead of being point-like. All the asymptotic condition and so forth can be applied to this case, and this thing is valid in this case. All right, so we have 4 complex vectors, K1, K2, K3, K4, with a 0 sum, and we can define their invariants. For example, zeta j is the square of kj squared. And there are some variables which have traditional names like s equals k1 plus k2 squared and so forth. And the sum of these variables, s plus t plus u is the sum of the zeta. Okay, now, since I have said that the domain is invariant under the Lorentz group, it will be possible to obtain points of the domain in some particular submanifolds of the space, and then we are assured that the final domain contains all the Lorentz transformed points from such points. And so all that I'm going to say takes place in a particular submanifold of the momentum space, which is defined by these equations. These equations say, first of all vectors have 0 fourth component, and the third component of all vectors is real, and a very important fact, which I don't see that I emphasized in this square, is that we fix the momentum transfer. So in fact, we fix this whole vector, K1 plus K3 equals 0, 0. The third component is given by minus t, and 0. So as you see, this follows from these equations.
Up to some normalization, because there's this factor.
No. K1 plus K3.
This sub-square root of minus t, which is missing.
Yes, sorry. It's square root of minus t. Okay. T is negative. No, this is. That is the situation. So we'll work in this submanifold. You see that all these components all these components remain fixed. But these vectors here, they're complex. Pi1, pi2 are complex. So we'll work in the space of two complex two-dimensional vectors. And in this submanifold, you have these relations hold. Zeta 1 minus zeta 3 is fixed. And since we want in the end to reach the case where the zeta j are equal to mj squared, this difference must be equal to the final mass difference. So we have these things, and so 2 out of 3 differences of square masses are fixed, but one is still free, and we can define a submanifold of this manifold, which is defined by fixing the last difference, zeta 1 minus zeta 2 equals m1 squared minus m2 squared. Once this is done, once you're in this submanifold, then there is only one of these complex masses which can vary. All the differences are fixed. Okay.
So you vary one mass.
I'm sorry?
One mass?
Yes, yes. Because, I mean, just as in Bogolyubov's proof of the dispersion relations, you interpolate between negative masses and positive masses. You fetch analyticity in the region of negative masses, you carry it to the region of positive mass. Okay, so the variables we use in this manifold are the light-like components of these vectors. So you have the vector pi1, which has components pi1, 0, pi1, 1, and u1 is the sum, b1 is the sum, as usual. Okay, now we also use invariant variables. These invariant variables are given by these equations. Z1 is the square of pi1, Z2 is the square of pi2, Z3 is the square of pi1 plus pi2. So these are invariants, and furthermore, you need a certain Lorentz transformation, which is given by this equation. So these are supposed to be new variables. So you can, starting from the variables you had at the beginning, namely u1, v1, u2, v2, you can map them to these new variables. But in order for these variables to be usable, you should also be able to look at the inverse map. The inverse map has some singularities. For example, you see here that you have a square root of z1, and here you have a square root of something else. This, in fact, this square root is equal to u2 v1 minus u1 v2. So you might think that you will not be able to use these variables in the regions where you have these critical points. And this is true of this in the case of this variable. In order to be able to use the variable square root of z1, in order to be, you will have to remove a cut, which is the cut where z1 is real negative. You remove this cut. But in fact, you can deal with this thing by symmetrization and anti-symmetrization, and so the fact that you have this square root is irrelevant. So the conclusion of this is that you can use these variables except on this cut C equal where Z1 in the negative real axis. Okay, well, let's dispense with this. If you look inside the manifold V, the space of the vectors pi1 and pi2, you look at their imaginary parts, you have some tubes. I mean, these are cells, like the cells I drew in before, but here, because the space is two-dimensional, you can make a drawing, a simpler drawing. So, I mean, for example, this line here says that the imaginary part of the vector pi2 is 0. And here, imaginary pi2 is in the V plus, here imaginary pi2 is in the V minus, and so forth. So the various tubes which appear in this pictures have this expression. So now, and of course,
Can I ask a question, Henri?
yes,
So this manifold V of t, it's a lower dimension manifold.
yes,
Is this going to be a problem?
no, you'll see. I mean, well, let me say something more. In fact, if you take the inside of here, the interior of a tube like this one, the interior of a tube like this one, by a very small analytic completion, you can show that the points, points which are interior to this tube are points of the final envelope of holomorphy. If you take a point of this considered as a submanifold of the space, take a point in this place, and it has a complex neighborhood in the space of all variables, which is a point of analyticity. Now, so we are going to use this manifold to find, we're going to make some completions inside this manifold, and the results will be points which will be able to transport everywhere by Lorentz, complex Lorentz invariant, and they will give points, bona fide points of the final domain. Okay, now in this space, in this submanifold, there are also regions of coincidence of the restriction to these tubes of the analytic functions. For example, the tubes A and B, for example, they're connected by a bridge which is the intersection of a complex neighborhood of this region R with a convex closure of A and B. So the region of coincidence, for example, the region of coincidence of A and B is given by these conditions. The regions of coincidence of A prime and B prime is given by this region. So whenever you have two of these tubes, there is a certain bridge between them, which is also composed of points which are points of analyticity in the final domain.
So this is just a projection of the primitive domain of holomorphy, or the restriction of the primitive domain of holomorphicity to this.
Well, I mean, in general, if you have a domain and an analytic submanifold, and if you look at the intersection of the domain and the analytic submanifold and make an analytic completion of that inside the submanifold, it is always a piece of the whole domain of holomorphy in the big thing. It's a general theorem which is not very hard to see.
Henri, I don't understand the relation of this manifold V of t with respect to primitive domain of holomorphy.
The manifold is a manifold.
But is it inside the domain? Is it on?
No, but it intersects the domain.
But it's bigger.
No, it's smaller.
But then why are we discussing this V of t? We already know that the function is analytic everywhere in V of t.
No, but we want to make some completions.
I see.
And it will be easier to make these completions in this smaller manifold.
I see. Thank you.
You know, analytic completion is a very laborious job. So you do what you can.
Completion means continuation.
No, completion means you have a domain, and in several complex variables, if any function which is analytic in the domain is in general analytic in a larger domain, which is common to all functions. And that's the envelope of holomorphy of the domain in question. It's something which doesn't happen in one variable.
But it's like determining the domain in which any function can be analytically continued.
Yes, exactly. For example, the tube theorem, you see, I mean, the convex tube theorem, you start with a tube which is not convex, and you know that any function which is analytic in that original tube can be extended to the convex closure. And so that's what we are after in this case. Okay, so all the tubes which appear in this picture have some bridges along some real regions of coincidence. And these regions of coincidence are defined by thresholds, which are given here, which are due to the fact that we consider now only the vectors pi1, pi2, and not all the components of the vectors. So you have new thresholds and also new values for the discrete mass hyperbolas. Okay, now this is the plan of the following. We have this picture with the tubes in the manifold V, and we are also going to restrict our attention to smaller things. For example, we'll discuss points which come from a submanifold like this. which are points on the boundary of the tube, but they provide analyticity. They provide some kind of analyticity. Then we'll go to this face here, and inside this face we'll try to solve an edge of the wedge problem, and we'll take the result and try to put these things together. Okay, so the points which are on the boundary of the tube, if you simply compute without doing any analytic completion, you see that these tubes provide a complex neighborhood of this set, namely, you see this set is, in this set, Z1 is real and smaller than the threshold. Z2 is real and negative. Imaginary Z can be arbitrary positive. And of course, the variable alpha can be anything. This is the complex Lorentz transformation, can be anything. So that these points on the boundary of the tube, I mean, it's a simple calculation. It proves that. Now we go to the colors have gone.
No, they're visible. For us, completely visible.
Good. So here, what do? We fix the vectors pi1 plus pi2. Vector pi1 plus pi2 is fixed, real, and it's fixed by fixing u plus equals v plus equals sigma. So this vector pi plus pi minus is fixed like this. It has a zero. It has a fixed. There's only a time component, and this is sigma. And okay, now we fix that, and there remains as a variable the vector pi1 minus pi2. Pi1 minus pi2 can be complex. Now one has to be a little bit careful, because while what I said about the tubes in the manifold V, that each point of these tubes was a point of analyticity in the global picture, this is not true in this submanifold, where pi1 plus pi2 has been fixed. Because here we are really on the cut. We are on the cut, pi1 plus pi2 squared equals something. And in fact, we'll fix sigma such that 2 sigma is greater than m1 plus m2. Okay. Nevertheless, we can look at what takes place in this phase, make some analytic completion in the vector pi1 minus pi2, and what will happen is that the points which we obtain in this way will be boundary points of the domain. So we know that by some discussion which I'll spare you, you know that the points which we obtain in this way are points which are limiting points of analyticity in the full domain. But, okay, so we consider having fixed pi1 plus pi2.
When you calligraphic M1 and M2, now I'm lost.
I'm sorry?
Calligraphic M1
Yes.
and M2, these are not the small m1, small m2, or the capital MJK before,
I gave the formula which relates them.
which I forgot. Okay.
I can perhaps go back
It for the function of t.
here.
Okay.
Here
Okay.
are the relations. They are bigger than the original threshold because you add some component.
Okay.
But in any case,
They are fixed.
so yes, so we have in the space of this vector pi1 minus pi2, we have an edge of the wedge problem. Namely, we have a tube which is just the forward tube of this vector, pi1 minus pi2, imaginary pi1 minus pi2 in the V plus. You have the past tube, imaginary pi1 minus pi2 in the V minus, and you have a region of coincidence. You remember that this region of coincidence was given by several conditions. And in fact, I'm on the wrong slide. Here. So, in this picture, you have the region of coincidence, which is the white region here. And here also, this white region. And these colored regions, I don't know if you see the color, they are the complement of the region of coincidence. And on the same picture is drawn the trace of the mass hyperboloids, of the one particle mass hyperboloids, which are here. And this point here, which is the intersection of these things, they correspond to the mass shell point in this particular submanifold. So, in fact, this point is what is interesting to us. And you see that it is very close to not being there at all, but it is there. Okay, so now when you have such an edge of the wedge problem in one variable, in one vector, you know the complete solution of this edge of the wedge problem. It is given by the Yost-Lehmann-Dyson representation. But here we won't need this because we wouldn't be able to use it, to use the full Yost-Lehmann-Dyson domain, and instead we'll use a small part of this region of coincidence, which is the green region, which is here. Is this visible?
Yes.
Okay. Now you see that in this region of coincidence, it is possible to draw an angle, which is this green angle here. And I mean, of course, this whole picture depends on the value of sigma, which I chose. But the aperture of this angle can be chosen independent of this. In fact, when sigma goes to infinity, theta tends to pi over 4. Anyway, you can choose an angle which is independent of sigma. And therefore, you can change variables to a variable. And also, another thing. Here you have this blue line. This is the submanifold where zeta1 minus zeta2 is fixed equal to this is why it passes through the physical point. And in fact, we'll work in this submanifold where this is also fixed. So I see that time is getting on. Anyway, now we had this green angle. In this green angle, we represent this green angle as a union of double cones. You remember that we solved the edge of the wedge problem with respect to a double cone, and so we know already some complex points that are obtainable from this. So this picture is in the real space, just as the picture before. So it's in the space of the x and t coordinates of the vector pi1 minus pi2. But now I'm going to look inside this line, and in this line there's a coordinate called x, and in this complexified coordinate, this double cone supplies us with a disk of analyticity, which is of the same size as, inscribed in this square. So, taking a new variable, which is this one, z, that's you see the remaining complex mass variable after we've fixed all the differences between the mass variable. There remains one, and we take this and now in this variable we obtain can you see this angle here?
Yeah, we can.
There's a blue angle here. That's what we obtain in the variable z. So now you see we are in this situation. From the previous operation, namely the boundaries of the tube, we have obtained, now I take as a new variable the variable s, which is connected to z3 by this quantity. And so from the boundaries of the tube, we got a kind of topological product like this. A neighborhood of these real points times an upper half plane in S0. And here we have a neighborhood of the real points here in the variable S, but an angle in this variable. Conclusion, we can make an interpolation between these two using the tube theorem. These are the new variables which we can use to make, and from this completion I again extract a topological product, and finally we get the following analytic completion. This is extracted from what we get. So we get the topological product of this fish-like object and an angle in the variable S0. Now, the variable U can be treated exactly the same way as the variable S by exchanging pi2 and minus pi2, for example. So we get exactly the same situation, but here, instead of choosing the part which is in the upper, I could have obtained an angle in the lower half plane. Here, that's what I do with the variable U. So we get this topological product and this topological product. This in the variable Z and S, and this in the variables Z and U. But U is not independent from S. You see, we have this relation, which is a reminder of S plus T plus U equals the sum of the masses. So S is given by this. So we'll take this and map it into the S plane. So in this way, we now have this situation in the S plane. Now, in the S plane, in the Z plane, we have this fish. In the S plane, we had this angle here, but in the U plane, it depends on where you are with Z here. So whenever Z moves in this plane, the corresponding angle in U moves around. All these sectors have a common intersection, and finally we get the picture which is here, the topological product of Z. Here, the angle we obtained in S, and here, the intersection of all the angles that we got in U. Now, we again go back to what we had before, namely, we had a topological product of a neighborhood of these points and the upper half plane in S, and there we have the picture which is here. We make a final completion using the exercise, second exercise I described at the beginning, and we find that we have for each value of Z, for all value of Z in the fish, we have the outside of this circle. For a given, now we place Z at the physical point, and we have not only that, but another sector belonging to this value of Z, and that is the final answer. You have for you have the outside of this finite region. And this is the crossing property. So I'm sorry to have taken too much time, but that's the end of my talk.
Thanks very much, Henri. I'm sure there are many questions.
So to get these results, you took this section of this Steinman sphere where you basically only considered 8 tubes at a time, right? You didn't consider all 32. So did anyone try more than that, or was this the?
Oh, no, I'm afraid the technical problems are discouraging, and as well as the result. But no, it should be possible to do better. It should be possible to do better. In particular, to find the correct size for this finite region outside of which you have an. Probably it is possible to do much better, but the people who worked on this were exhausted at that time.
But what determined the final success of your story? So you chose this manifold view of T. It's not clear, so what was the intuition that led you to consider? Was it very natural choice, or were you lucky to have chosen? What was that led you to that?
It's sort of natural.
Yeah.
It is sort of natural because you see, you want to fix T. You want to fix T real negative. So what can you do? You fix the vector K1 plus K3 space-like. And then you look at what happens in the orthogonal space to that. It's sort of natural. But I don't say that being more clever, you probably might do better, as usual.
But what I liked about your presentation is that you kind of explained with one of your first examples is why are we landing on this region which is outside of some big region. So that was clear.
Yes, because you succeed in having the sides, you see.
Yeah.
And there are several ways of getting the sides, but from the tubes, that is the negative mass business. I mean, you go to the tube, you fill the upper half plane of S. So now you interpolate between those two.
Is your final domain has homomorphically convex boundary everywhere, or it's still possibility to extend it?
Oh, there is certainly.
It's not final yet.
Of course. No.
I see, yeah, just some functional.
No. I mean, there is only one domain which has been. That's the result of Whiteman and Chilean for the 3-point function in X space. That's the only known complete.
There's a question from Balt.
I was wondering if this is the S-plane, there should also be the cuts, of course.
Yes, the cuts are there.
Are they anti-trend?
I mean, this is a cut. This is a cut. This is the S cut. I mean, it occurs even when there are dispersion relations.
Yes, yes. So I was wondering where they start, but they start exactly at S1.
No, they start lower. They start lower. I mean, they probably start here or, no, they are lower. But on the other hand, something which I had planned to talk about in my first lecture, but I didn't get to that. In one of the results one can prove in the case of the four-point function is this, that for every physical point, you have a cut neighborhood of analyticity, namely you have some real physical point, P, let's say, in the full space, and then there is a complex neighborhood of this point, and from which you subtract the cut. This is the cut which, for example, in this case it's the S cut, but there is also the T cut, the U cut, and so forth. So the same happens. So, in fact, if you have another physical point here, for example, you know in advance from this theorem that you have some neighborhood there. And this is not true in functions, in n-point functions with n arbitrary. It's not true.
It's not known to be true, or
It's known not to be true.
known not to be true? And should I not have some kind of crossing symmetry, like symmetric property? Like there's an extra wedge going out to the left, but should there not, or an extra strip on the left? But
No, I don't know. No, but I mean, of course, this is not satisfactory because you don't know the dimension of this potato.
And then finally, so if t is strictly negative, then between if I take identical particles for simplicity, there's a gap between s equals 4 and s equals physical.
Yeah.
So for that gap, no analyticity result.
No. Except in the cases of dispersion relations.
Yes.
Right.
Yeah, so, yeah, it wasn't clear, but maybe you mentioned it. So this size of this region does depend on t.
Yes.
So you just take the intersection when you vary this z so that you come to the physical mass, and then whatever is the common intersection is this.
Yeah.
But it still depends on t.
Yes.
If there are no further questions, let's thank Henri again.